a great pleasure to speak at this nice event in honor of Monique Laurent. I indeed submitted a very ambitious title, talking about proving inequalities and talking about iterative methods in general. But what I would like to do is just focus my thoughts on one specific method that's easy to understand. And so then it's easier to parse some of the results. So this method dates back to Cauchy, and it's called the gradient method. And it's particularly simple. I think everybody who's ever had a course in nonlinear optimization will have studied this method. So the idea is that we aim to minimize some input function f. It's a function of n variables, a real valued function. We are given a starting point in Rn, which I call x1. We are given a number of steps that we wish to perform of this iterative method, capital N. And we are given step lengths, which are just positive scalars. And then we are doing this following iterative process. The new point xk plus 1 is the old point xk, updated by this second term here, which is just the minus gradient at the old point xk, minus the gradient of f at the old point, and then multiplied by this step length tk. Okay, so this is a very simple iterative method that aims to minimize a function of n variables. So the method is due to Cauchy, and he studied this near the end of his career in 1847. And he described it in a very short note, a 3-page note that appeared in that year. And you can easily translate the French. It says it's a method, a general method for the resolution of systems of simultaneous equations. So in modern language, we would call this a nonlinear regression problem or a nonlinear least squares problem. And what Cauchy said about this in his note is that, well, about the convergence is the new value of the objective after one step is not the minimum. One can deduce, again, proceeding in the same way, a new value still smaller. And so continuing smaller and smaller values will be found, which will converge to a minimum value. So basically all he's saying it's a descent method. So the function value will decrease or not, will be non-increasing at every step. And it's bounded from below because it's a nonlinear least squares problem. So it will converge to something, but we don't know what. So that's, Cauchy left it there. And if you want to make more precise statements, you will have to limit yourself to certain classes of functions. It's just too general to consider all differentiable functions that you might encounter as input. So the class of objective functions where one can say interesting things is called the class of bounded curvature functions, or functions of bounded curvature. And these functions are also known as hypoconvex functions. So I will explain to you what these objects are. But first of all, a special case of them are the L-smooth functions. And for our purposes, I'm only going to speak about continuously differentiable functions. So because we are studying the gradient method, we need the gradient, and I'm going to assume the gradient is a continuous function. But if the gradient is in fact Lipschitz continuous, then we speak about an L-smooth function. Okay, so this is the Lipschitz continuity condition for a function, and so a function that satisfies this gradient condition is called L-smooth. And then we are minimizing the function, and so it makes sense for us to assume at least that we will have a global minimizer. I will denote it by x star, and it has a corresponding function value f star. So we are trying to compute the values, the vector x star and f star if possible, and we will see how well the gradient method performs with these considerations in mind. So there's a very nice property of L-smooth functions that we can always use. Is called the descent lemma, and it basically tells us that the distance from the optimal value of the function at the point x is lower bounded by this expression here. So basically, the way you prove this is by showing with a simple exercise in calculus that you can always take a step in the negative gradient direction of length 1 divided by L, and then you can always get at least this much reduction. Okay, so this is a general inequality that's true for all L-smooth functions, and this is something that we are going to use. So now moving to the larger class of bounded functions of bounded curvature, we are staying with continuously differentiable functions. So we say a function has maximum curvature if the function here, which is just the norm of x squared times the constant L divided by 2 minus f is in fact the convex function. Okay, so this might not be too intuitive, but this corresponds to a function being L smooth. So the next thing that we can require is, so this is the first was the maximum curvature. Now the minimum curvature, a function is said to have minimum curvature mu if we can subtract some quadratic function from f and still obtain a convex function. So in particular, we require that mu is at most L, but it can take negative values as long as these are finite negative values. So in particular, what we can see, if mu is equal to 0, this implies that f is a convex function. So this includes the class of convex functions if mu is equal to 0. And we will have a notation for this class of functions of bounded curvature, which again are also called hypoconvex functions. So we have these parameters mu for the minimum curvature, L for the maximum curvature. Domain is Rn, so we have this notation f mu L of Rn. If we have mu is 0, we already said we're speaking about convex functions. The L we said corresponds to L smooth. And if mu is minus L, so then we are talking exactly about the class of L smooth functions. And if our function, in addition to being continuously differentiable, is also twice continuously differentiable, then it has a Hessian. And then the condition f belonging to this class is the same as saying that the spectrum of the Hessian lies between mu and L. So all the eigenvalues of the Hessian lies between these two values. Okay, so this is for me a very easy way to think about hypoconvex functions. These are the functions, if you think about twice continuously differentiable, where the eigenvalues of the Hessian lie inside a certain interval. So one other important thing that we should notice right away is that these functions are defined in terms of this norm. And if we change the norm, then we change the class of functions. So these functions are not invariant under changing the norm, or in our case, we are going to work with induced norms. So if we change the underlying inner product on the space, we change the function class. This is also important to remember. Okay, so what tool am I going to use to analyze the method of Cauchy for these hypoconvex functions? So the tool that I want to describe, because it's quite fits with the research interests of this meeting, namely semi-definite programming, was pioneered by Mark Taboul and his PhD student at that time, Yoel Drori. This was in 2014. And their idea was to formulate the problem of finding the worst case input for the gradient descent method as the analytic solution of some optimization problem. Okay, so once again, we have the Cauchy algorithm. The input is some function f, and we're going to restrict it to this class. And we're asking ourselves, what is the worst case input? Okay, so for which function gives the worst case performance of the Cauchy method? And their insight was sometimes you can write this problem of finding the worst case input as a different optimization problem which is tractable, and in particular it's a so-called semi-definite programming problem. Okay, so what is the idea? So let's just try and see how far we get if we just try to formulate the problem that finds the worst case input to the Cauchy algorithm. So we can think of different objectives that we might have if we perform n iterations. So we would like the gradient to converge to 0, for the gradient norm of the iterates to converge to 0. So we can say the worst case scenario is obtained if f is such that the gradient after n steps is a maximum, or if the distance in function value from optimality is a maximum, or if the distance from the minimizer, the global minimizer, is a maximum, or sometimes it's appropriate to use a weaker notion of the convergence of the gradient norms to 0. So this corresponds to just saying that there would be a subsequence of points for which the gradient norm converges to 0. Okay, so these are all legitimate possible criteria for defining what we understand as worst case performance for the Cauchy method. And then we would like to add some constraints. First of all, we need to bound the problem so that otherwise we will not get interesting solutions. So we're just going to introduce some parameter, fixed parameter delta, and say that the function value at the starting point minus the optimal value is bounded by this. Okay, so this is without loss of generality. So we just consider the class corresponding to a given delta. Then also we say that, okay, we're going to generate more points, x2 up to xn plus 1 after n iterations. And these points have to correspond to points generated by the gradient descent algorithm with respect to our function that gives us the worst case performance, and with respect to our chosen starting point. So our starting point is going to be a variable in finding the worst case input as well as the function. So it's a bit confusing to understand this optimization problem. The variable is the function from this class and the starting point. The givens are these parameters just to bound the starting situation. And then these parameters for my class of functions, the mu and the L. And then the number of steps I want to take and the step lengths that I'm going to use. These are all the inputs, or these are the parameters. So it's a difficult optimization problem because it involves a variable that lies in infinite dimensional space, this set of functions. The set is a very complicated set. It has basically no nice properties. So we do not know how to deal with that. So we would like to transform this optimization problem into something more tractable. And then the key idea is that this can be reformulated as a semi-definite programming problem, which is tractable, by representing this function class via interpolation. So somehow we're going to bring this infinite dimensional space down to finite dimensions by changing this membership problem into an interpolation problem. Okay, so how does this interpolation problem work? So the idea is that if we are given an index set, it's denoted by I, and these index sets are just given some data triples. So we're given some vectors xi, some more vectors gi, and some scalars fi. And basically we are asking if this data corresponds to a function from the class that we're interested in. So the x will correspond to points in the domain. The gi's will correspond to the gradients at those points, and the fi's we would like to correspond to the function values. So given such data, the question is, do these things correspond to some function f in our class of interest, in the sense that these fi's are just the function values, and these given gi's are just the gradients at the given points xi. Oops, so this s has changed from the I has changed into an S. My apologies. Okay, so this is the interpolation question. And if the data can be interpolated by a hyperconvex function from our class, then we say that the data is f mu L interpolable. Whoa, mouthful. Okay, so here is the key result, which is really the main tool that is used in this reformulation. This is an interpolation theorem that was developed over a number of years, and this was due to a group at Louvain-la-Neuve, François Glenier, Julien Hendricks, and at that time Adrian Taylor, their PhD student. So they had 2 papers about this, and this has been finalized in this form I'm showing here just this year by François Glenier with the next generation of researchers. And what this theorem says is this condition that the data set can be interpolated by something in our function class is the same as some finite set of inequalities holding for this data set. So basically, we can answer the question with certainty whether the data can be interpolated by a hyperconvex function by just checking a finite set of inequalities. So basically, for all points, all distinct points I and j in our all distinct indices I and j in our index set, we just have to check that this inequality is true. So where does this inequality come from? Well, this just corresponds to a known inequality for hyperconvex functions. So just to make it a little bit easy for ourselves, if we think about convex functions, then mu is 0, so we don't lose these terms. we lose this part here. And then if we just let L go to infinity, because the theorem is actually true also for L infinity, then everything on the left-hand side becomes 0. And we just left with this thing here must be non-negative. But this thing here being non-negative is just a very well-known inequality for convex functions, right? The difference minus the function values minus the gradient times the difference in x's is non-negative. So this is a standard inequality for differentiable convex functions. Okay, so you can just use the definition of the hyperconvex functions using these two definitions of convexities, and you can prove that this is a necessary condition, but we just have to check it for all the data points, and then we know the data points can be interpolated by something from this class. Okay, and the nice thing is the proof is constructive. So basically, if you give me the data set and it can be interpolated, I can construct a function that does interpolate it. It's also important for us.
Etienne,
Yes?
does it matter whether L is positive or not?
Yeah, L is positive, always. Or non-negative, to be precise.
But
Yeah.
mu can be negative.
Mu can be negative for now, yeah. Yeah, so indeed, it's, indeed, it's not shown in the nested loop, that's right. So it's not clear here, but L should be non-negative.
Positive.
It can be 0.
Because L is you divide by L. So
Okay, I divide by L, then that's positive. Okay, so just to list the historical development. So basically, these were the two papers from 2017 by the Le group, and it has just been updated. So they first did the case where L is finite and mu is strictly positive. These are called the smooth, strongly convex functions, of course. Then it was extended also to the L smooth functions. So that in that case mu is minus L, and then of course, and now the general case where mu can be negative but not necessarily equal to minus L. This is the most general hyperconvex case, and it was only settled this year. So there's a nice development here, and then the thing I showed you is really is a theorem from this year. Okay, so and then finally we end up with something which is I claim to be tractable. So we still have our choices of objectives from before, and now we have no longer variables that are functions from this function class, but just some vectors. So we will now have variables which correspond to points, unknown points xk generated by Cauchy's algorithm. The gk is corresponding to the gradients at those points, and the fk is corresponding to the function values at those points generated by the Cauchy method. Okay, so let's say we want to minimize the distance from optimality in the function value, so we choose this objective. The worst case is where this is a maximum, so that the function value after n iterations minus the optimal value is as large as possible, so that's the worst case function. The function has to be from this class of hyperconvex functions, and that is modeled by these inequalities here. And remember again, so this is tight. So whenever we will have a solution to these inequalities, then we will be able to construct a hyperconvex function that matches these constraints.
So M star or X star assumed to be known?
No. No. We don't. We can fix it without loss of generality. Yeah, but I mean, yeah. So that's the right answer. You can fix it without loss of generality, even to 0. So, but I mean, this is just for the exposition. So then basically, what else do we have? We have that using the method of Cauchy, the new point is the old point updated by the step length tk in the minus gradient direction, and we can also add this inequality from the descent lemma. It cannot hurt, so it might help us. And then we had the starting condition that just bounds everything nicely. So the starting function value is bounded from the optimal function value by this given parameter delta. And the gradient at the optimal solution is of course a 0 vector. So now we have variables again, these xk's, fk's, and gk's. And the parameters are as before. The parameters for the hyperconvex functions are delta, the number of steps, and the step lengths. And the whole point of this is now this problem is tractable. This is a so-called semi-definite programming problem, and it can be solved to any fixed accuracy in polynomial time. So if you want to solve this problem numerically, you can do so, provided that this this is small enough to fit in your computer. And the size of this program is determined only by the number of steps that you take, this capital N. So why is this a semi-definite program? It's because these unknown vectors only appear in inner products. So for example, here we have these unknown gi's, gj's, and xj's and xi's, but they appear in inner products. So instead of treating them as the variables, we can just treat the inner products as variables. And these, so we can just say these inner products are the entries of an unknown gram matrix. Okay, so that's why this is in fact a convex optimization problem in disguise. We can just replace these inner products by entries of an unknown gram matrix. And the very nice thing about that is we no longer see the inner product then, and we also no longer see the number of variables. So we don't see the dimension of the problem anywhere. And finally, this solution of this optimization problem will exactly give us the worst case performance, provided that the number of variables is large enough. In particular, so this n determines the size of this problem, and as long as the number of variables is large enough, then we will have an exact correspondence. So this is a precise reformulation of the worst case performance of the Cauchy method for hyperconvex functions, and with the property that it's exact and tractable.
Can you remind me for the equation with the xk plus 1 equals xk?
Yeah, this is just the Cauchy method.
No, I understand. But as yeah, right. Just in terms of representing it as the STP.
Oh, we will eliminate the x variables. So we can just eliminate all these variables. Okay, so yeah, that's a good point. So I said everything appears in a product, so that has to be true. We get rid of this by just using these equations to eliminate the x variables. Yeah, true. Okay, so what can one then get as results for the worst case performance of the method of Cauchy for these functions? So we start with the case where mu is positive, and so we have a strongly convex function, and L is finite, so we have L smooth strongly convex functions in this case. So what we could show in 2017 is you can then solve this semi-definite program in closed form, not just numerically, but you can get the closed form solution. And then you find that after n iterations, provided that you use the step length 2 divided by mu plus L at every step, so you just use one step length, this one, then after n iterations, then the function value, distance from optimality, is the old distance at the start reduced by this factor here. So basically at every iteration you get a reduction by L minus mu divided by L plus mu, which is smaller than 1, squared. So this constant here determines the so-called linear rate of convergence. So the linear rate of convergence of the method of Cauchy was known already for strong L-smooth strongly convex functions, but this constant was not known in general. So we just basically fixed this constant. Okay, so in particular, this exact result was known earlier, but not for the whole class, but just for quadratic functions, which belong to this class of hyperconvex functions, which are strongly convex, and it's also tight. So the interesting thing is also this exact same result with exact same error bound holds if we do not use this fixed step length, but we select the steps through exact line search. Then we also get exactly the same rate of convergence. And this was shown in this paper. And what is this quadratic example? Or what is the example that shows that it's tight? So it's a simple example shown here. So it's actually a family of examples for any n. And what we do is we just, it's just basically a quadratic, homogeneous quadratic function with a diagonal coefficient matrix. So the lambda 1 is just the mu for our function class. The last lambda is just the L for our function class. And the other lambdas are in between. The values do not matter. So we start at the point where only the first and last coordinates are non-zero. And then basically throughout the algorithm of Cauchy, we will stay in the same plane where these intermediate coordinates are zero. So it all reduces to a two-dimensional problem, which is indicated in this drawing. So these are the steps of the Cauchy method. And the interesting thing here is the step lengths are indeed as indicated. So the step lengths here are precisely those step lengths, but they also happen to be exact line search step lengths in this, for this example. And you can just see this graphically because the step takes us to a point which is tangent to the contour. So here again, it's tangent to the contour. So for this example shows, establishes the worst case behavior for both fixed step length of the shown size and the exact line search. And the other side is shown by the semi-definite programming bound. Okay, so that is the strongly convex L-smooth case. And now just to say, how do we find this closed form solution of the semi-definite program? So it's clear how you would do it numerically, but how do you do it analytically? And the answer is just this is more of an art than a science. So basically what we do is, we aggregate the constraints in the semi-definite program by just finding the optimal Lagrange multipliers of a dual. So basically we find the optimal Lagrange multipliers, which are the optimal solutions, optimal variables in the semi-definite programming dual problem. And how do we find these multipliers? Well, we solve the SDP numerically for many choices of the parameters. So we are just getting some data, and then we know that these optimal multipliers, they have to be algebraic functions of these parameters. So we just do some reverse engineering and try to guess the answer, and then finally we guess the answer, and then we just verify the correctness through symbolic calculations. So so it's I wish I had a simpler answer. I often get asked, how do you find these complicated expressions? Well, there is no simple answer. You just keep trying. Sometimes you're lucky and you find the closed form solution, and sometimes you cannot. Okay, so then the next thing that I would like to talk about, which is for me very interesting, is that this function class f mu L depends on the reference inner product. So why? Because it's defined in terms of a norm. So if we have an underlying reference inner product, of course that induces a norm. And so let's just try to understand what happens. So first of all, we have to understand that the gradient of a function depends in some sense on the underlying inner product on the space that we use. So in terms of Fréchet derivatives, the gradient at x is a unique vector g of x that satisfies this limit equation. Okay, this is just the standard definition of a Fréchet derivative. But what is unique here about this derivative? So basically, this linear operator here is unique in the sense that if you view this as a linear operator acting on h, so this is a linear function of h, this is the unique part. But so if we would change the inner product, the gx part will have to change to make it invariant. So this is an important thing to understand. And so basically, if we had the Euclidean inner product, then the gradient we get is just the vector of partial derivatives. So this is what the students learn in calculus. But I mean, this is a limited view because this is really for the standard inner product. So basically, there are infinitely many inner products, of course, on Rn, but they all arise through linear positive definite self-adjoint linear operators, self-adjoint with respect to the underlying inner product. So if we can define a new inner product in terms of the reference one, and we note this by the operator, so then we just do this instead of using the identity there, and then we get a new inner product. And all inner products arise in this way on Rn. So why is this interesting or useful? Well, the idea is that, how does the gradient change? So if we change the inner product up here to the B inner product, and it's easy to see we will have to change the gradient to B inverse G to make this thing invariant. And so if we change the inner product to the B inner product, then the gradient changes to B inverse times G. So basically we can, instead of just analyzing the steepest descent gradient of partial derivatives, we can analyze steps using anything of this type for a positive definite operator B. Okay, so why is this interesting? So it's interesting because then we can analyze Newton's method in this way, not just the Cauchy method. So if a function is twice continuously differentiable, then it has a Hessian. So and then this self-adjoint Hessian, and this Hessian satisfies again this equation for the Fréchet derivative. And then basically then the idea is that we can now fix one point in the domain of a function, and we define as a positive definite operator, we take the Hessian at that fixed point. And what happens then is that the gradient changes to this operator, which was B inverse before, but our special trace of B is this Hessian at the fixed point. And if you look at this thing, this is precisely the Newton direction, but with a minus sign. Okay, so we can obtain the Newton direction as a special case of the gradient by just changing the inner product. And so we can analyze one step of Newton's method by using a suitable inner product. Why only one step? It's because, you know, if this Hessian will change with x, so we're just fixing x. So if we just look at what happens at the fixed x, we can analyze a step of Newton's method. So basically, the interesting question to answer still is then what class of functions, what happens to our function class f mu L? What happens to our class of hyperconvex functions if we play this game with the inner products, and what are these values of mu and L? So I mean, so how do we interpret these results that we just obtained for Cauchy's method for this function class? So the thing to remember, which I already mentioned, is a function belongs to this function class if and only if the spectrum of its Hessian is basically contained in this interval between mu and L. And up to now, I only spoke of all of Rn, but you can also limit this to some domain, and then this is you can consider this definition of the function class with this more general definition. So okay, wait. Whoa, sorry, I went to wrong thing. Yeah. Okay, so the first thing we have to understand is, you know, since the gradient changes with the inner products, and so does the Hessian. So basically, if we change the inner product from the standard one to the one defined by the Hessian at the fixed point, then a Hessian at the point y just becomes this operator here, which is just denoted usually by hxy. So the subscript x just reminds us that we have to multiply it by this linear operator from the left. And the idea is now that our function class f mu L corresponds to a known class of functions which are called self-concordant functions. And just to make this believable to you is just to tell you what is the definition of these self-concordant functions. So basically the self-concordant functions, a function is called self-concordant if for any point in its domain and any point y in a ball around it, the ball defined by this inner product of ours, defined by the Hessian at x. So then this must still be inside the domain, and the spectrum of this Hessian must be contained in this interval. Okay, so the spectrum being contained in the interval is exactly what we're talking about. So we're going to associate this mu with this value and this L with this value. Okay, so I am going slightly slow, so I'm just going to jump to the conclusion of this. So basically, the worst case analysis of the gradient descent method applies here. We just have to reinterpret our function class and our inner product, and then we can analyze one iteration of Newton's method. And the function class that we can analyze is a class of self-concordant functions. So if you want to read more about this, this is some work we did published in 2020, and it's useful because Newton's method for self-concordant functions is used in the complexity analysis of interior point methods. So this is we could get some new insights by applying this procedure to these self-concordant functions, to Newton's method for these self-concordant functions. Okay, so just then I'm just going to speak to you to just a few more results, just quickly. So L-smooth functions were also special cases of hyperconvex functions, and then just something that I did recently with my postdoc and Muslim Zamani and PhD student Hadi Abazadeh Payfasti was to show that in this case we can look at the different objective criterion. So if you remember, one of our criteria was we tried to minimize the gradient norm, but in this case we're talking about just L smooth functions, so these need not be convex. So in this case, trying to find a convergent sequence of these norms is unattainable. So I think Amirali will tell a bit more about the complexity of finding stationary points later. So the best thing one can hope for is to say something about this objective, which is to say that we have a lot of iterates, xk, and then at least the smallest norm of the gradient taken over all the iterates will be no larger than a given value. And this value goes to 0 as 1 over the number of iterations, which is big N. Okay, so again, this basically the sublinear rate of convergence was known before. This basically that this is order 1 divided by capital N, but we again established the exact constant. So this constant is exact. And so how you know that it is exact is, again, we can just construct an L smooth function that matches this bound exactly. And in this case, I don't give the details. I just give a picture that corresponds to specific values. So in this case, L is 1, the delta is 2, the number of steps is 4. And these are the points 1, 2, 3, 4 that we generate during the algorithm. All the step sizes here are 1 divided by L. Sorry, I should have said this. This result is for fixed step sizes, or at least the result that I'm showing. And so indeed, for this example, we get exactly the same bound as in the theorem. So again, we can get the tight convergence rate for L smooth functions for the special case where the step length is 1 over L. Okay, so I want to skip this part. I'm just going to say that we can keep playing with this function class. We can keep adding new features to it that help us to derive new results. But I mean, this is something that you can read more if you wish. So just there is something called the Polyak-Łobaszewicz inequality. And if you are interested in reading how this helps us to prove a better convergence rate, you can just look at this recent work with Zamani and Abbaszadeh Payfasti. So the only thing I want to mention is this condition, which is called the PL inequality, is weaker than convexity, but it still helps us to prove something faster than a sublinear convergence rate. So if you just glance at this error bound here, this constant here is something smaller than 1, so it defines a linear convergence rate. And so this is something better than you can get just for L smooth functions, for example. So this is not convex, but it still allows us to get some linear rate of convergence. And it's the weakest condition one can impose instead of convexity and still get this linear rate of convergence. Okay, so then I just would like to wrap up by just saying that, this very recent paper by Glenier and Rutaro and Patrinos, they have more tight results for the gradient method for hyperconvex functions. I didn't cover all the cases. And of course, I to keep things a little bit understandable, I only talked about the method of Cauchy. So you can also analyze other methods like ADMM, the convex concave procedure, or DCA. You can do accelerated gradient methods. You can study stochastic gradient methods, operator splitting methods. So there's a whole literature about this already that I cannot cover. One thing I would like to say is there is a very useful piece of MATLAB software due to these authors, again, Taylor, Hendricks, and Glenier. And this software does the numerical calculation of these worst case convergence rates by solving these semi-definite programs that I've shown to you. So this is actually extremely useful piece of software. I use it to teach my graduate students. I think some students here have actually used it to do some assignments. And then if you want to learn more on an introductory level about this topic of performance estimation using semi-definite programming, the PhD theses of Yuval Drori and Adrian Taylor are both online, and these are really excellent pieces of work that introduce the topic. So then finally, I would like to say congratulations to Monique. I do not have a picture of when Monique was awarded the CWI fellowship, but fortunately Monique has many fellowships, including the Royal Dutch Academy of Sciences, or KNAW in Dutch. And this was taken on the occasion when she received the KNAW fellowship. So Monique, heartfelt congratulations, and may there be many more. Okay, that's it. Thank you.
Does this work? Yes. Yeah, so Etienne, thanks a lot for this beautiful talk, and thanks also, I mean, it was perfect on time, so it was a fantastic talk. I think very nice. So actually, I forgot to mention, like, if you have questions, then it would be actually nice if you could, raise your hand, and there's a mobile microphone that walks around and kind of will give you the microphone. So we have actually time for some questions. Please go ahead, let us know if you have any questions to Etienne.
Hello, thanks. Etienne, wonderful. I have two questions, actually, if you allow me to ask them. So the first one would be, immediately from the start, you started defining your classes of functions with respect to the L2 norm. But there's also a lot of work on L-smooth functions with Bregman distances. I guess you can accommodate this as well by just playing with the norms, right?
I think we discussed this in the past. So, I mean, the thing is just that if these are induced norms, yes. Well, I mean, so but you see, if you use more general metrics than induced norms, then your interpolation theorems don't work anymore. Okay. So the interpolation theorems are independent of the inner product as long as you interpret the gradient correctly.
Right.
But if you go to other metrics that are not induced norms, then I don't think things carry through.
So for these functions, your technique would not apply at the moment?
No, because you don't have these interpolation theorems.
Interesting. Yeah. Okay. And second question, more out of curiosity. So the last result on the Pierre-Yoshiers inequality, can you quantify the mu p? Can you compute it somehow? Because this is usually the hard part, right?
Yes. No. I mean, I think these things, you can ask the same of this mu and L for the hyperconvex functions. I think these are theoretical studies. In practice, calculating these constants are harder than the problem that you are interested in. So you restrict yourself to the class, and that's it.
Okay. Thanks.
Yeah. Thank you. So, any other questions from the audience?
I had a question on the interpolation theorem. You said you can restrict it to a domain that isn't the whole thing, but is it the same theorem?
No, indeed. So I skipped the details, but it's a very good question. So you have to be more careful. You only have weaker conditions. So it's not. You cannot simply get the same interpolation condition when you restrict to a smaller domain than all of Rn. You have to adapt it slightly, but I just swept this under the carpet.
But there is some result.
Yeah, there is a result. So this paper I mentioned in connection to the Newton method develops this theory.
Yeah, there's another question here.
Does your class of functions exclude multiple local minima?
No. Well, I mean, L-smooth functions can have multiple local minima. So, yeah. In the most general case, no, it doesn't exclude it. But I mean, of course, if you go to positive mu for strongly convex functions, of course, that's a unique global minimum then.